And then for the Laplace transforms, does that include general transforms, or does that extend all the way to step functions as well?
All the way to step functions. Yeah. You can definitely expect a problem to be, to involve something like that, like a differential equation that you just solve for Laplace.
Okay.
Yeah.
Same combined, or
what do you mean combined?
You said the OD that can be solved with Laplace. Are you saying
yeah
combined, or you want in each?
Combined. Yeah.
Am I ready for it? I need some work on that one. There's so much memorization. Like I can have all the equations, but just maybe have a little cheat sheet with this.
She says, which choice was eliminated. Well, first that the freehand is just the last stuff we do.
Everything from exam to.
That's the little thing. Just like literally outside your team. Yeah, there's a small question. Presentation, like it was okay. It was only great.
I think just repetition and knowing when to apply what equation. So I'm just gonna go through all the examples she gives. I talked about the examples that we did in class, plus the homework ones are solid setup for the exam. And then it shows the reviews, some of the stuff in the previous exams for the multiple choice.
All right, it's 4 o'clock. Let's go and get started. All right, so for one last time, good afternoon, everyone. How's everyone doing today?
Good, how are you?
I'm good, good. Thanks for asking. Okay, so it's just the last day. So like I promised today, we're doing a review session for the final exam. One problem, unfortunately. So I put the poll on Canvas for you guys to vote on what topics that you would most like to see. And of course, I did not think to check Canvas until a couple hours before the class. But I'm sure you guys have heard Canvas has been hacked, apparently. So nobody can access Canvas right now. So I don't have the results of the poll. So these 2 topics I've chosen just based on history. So last couple semesters when I've taught this class, these are the 2 topics that kind of show up consistently for the final exam, which is Laplace transforms and all the most recent stuff with probability and stats. So if the results are something different, I apologize. Once I do have access to Canvas restored. If the results are something different, I think probably what I'll do is I'll record a review session kind of just from my home and just post that as a separate video. But I did have to have something to talk about today, so I'm just going based on what's happened in the past. So Laplace transforms we haven't seen in a while. There's a lot to cover with Laplace, honestly, but I'm just going to focus on the stuff you're going to need for the final, which is solving differential equations with Laplace transforms. Okay. So we'll probably do that for the first 45, 50 minutes, and then we'll do a more quick review of probability and stats after. Okay. All right. So just a reminder, our final exam is next Tuesday here in this room, E22. It is going to be a 2-hour exam, so it's going to be from 5 p.m. until 6:50 p.m. You're allowed 2 cheat sheets, and so 2 8.5 by 11 sheets of notes you can bring. You can put anything on it. You can bring your cheat sheets from the first 2 exams, although I wouldn't recommend it just because there's a lot of topics from the first 2 exams that aren't going to be on the final. And so I do recommend that you make your own cheat sheets from scratch just to make sure you have you make use of that space as much as possible. Okay. Besides that, you can bring a writing utensil. You can bring a calculator. I haven't written the exam yet, but a calculator I think is definitely safe to bring for sure. Okay. All right, and good news for you guys too is that you guys are my only final exam that I'm giving next week, so I should have them graded pretty early, and so by end of next week I should have them all graded out. Okay. All right. Any questions I can answer before we get started for today? Yes.
Is the hack, is homework going to be pushed back a little bit?
Sure. Yeah. So let's push back the due date for the homework. Was it due today? I don't remember. Tomorrow. Okay. So let's push it back to Friday. Sure. Yeah. So I don't know how long Canvas access will be down, but for however long it's down, we'll push the due date back by that. So at the very least, it'll be due Friday. Tomorrow's Friday. I would do Saturday. Yeah, Saturday. My sense of time is all messed up. All right. Any other questions? Okay. All right. So let's go ahead and get started. Okay. So first topic today is going to be Laplace transforms. Specifically, we're going to talk about solving differential equations with Laplace. Okay. All right. So we spent quite a bit of time in this class talking about Laplace transforms. So I think it was at least 3 weeks. So this was very, very early on in the semester. But really, the whole reason we pursued this whole Laplace transform was to give us an alternate way to solve for differential equations. Okay. And so for those of you that are in mechanical engineering, this is primarily what you're going to be using it for. So 308 is the prerequisite for vibrations, 431, although it has a new name starting next year, 323. But this is one of the main takeaways from this class that you're going to need to have in order to go into vibrations. Okay. And so the process is the following. So we start with a differential equation. Right. And so we're only looking at differential equations with constant coefficients. And so we have, y double prime plus by prime plus ky is equal to r of t. Okay. Where y here is our variable of interest. That's what we're solving for. B and k are just constant coefficients. And r of t, of course, that is our non-homogeneous forcing term on the right-hand side. Okay. We also have our initial conditions. We have y of 0 is equal to y naught, and then y prime of 0 is equal to y naught prime. Okay. All right. So that's a starting point. So that'll be given to you in whatever problem that you might have. Okay. Next step. Right. So what we're saying with Laplace is that we essentially want to solve our differential equation in the Laplace domain. Without having to do any kind of, of those tricks that we did with differential equations. So second step here is we're going to take the Laplace transform of the entire equation. Okay. All right, so remember, we apply our Laplace operator to every single term in this equation here, okay? And remember, since Laplace transforms are a linear operator, we can then apply the Laplace transform individually to each of the terms in this expression, okay? And any constants that we have, we can just kind of factor in, okay? Okay, so we'll go over we'll kind of review exactly how to do this when we do an example, but just know that, eventually, right? You're going to be able to solve algebraically for some y of s. Right. So that's one of the main benefits of Laplace transforms is that instead of solving a differential equation where you have to do things like undetermined coefficients, characteristic equations, things like that, you can just, use algebra and solve for whatever your solution variable is. Okay. Right, and then final step, once you have your expression for y of s in the Laplace domain, you then take the inverse Laplace of that in order to solve for y of t, which is our goal here. Okay. So when you look at it from kind of 10 miles away, it's fairly straightforward, but just as with anything in math, they say the devil is in the details, right? Right. And so some of these details involve, how do we even take the Laplace transform of this type of function, right? So there is an equation that we can use to take Laplace, right? So we did do that a few times in the class, but generally speaking, from a practical point of view, most of the time you're going to use our table of Laplace transforms. Right, so you're basically going to look at a particular function, look at its functional form. You're going to try to find a matching entry in the table, and then use that table to perform the Laplace transform quickly. Okay, and you're going to do that here as well, right? So to take the inverse Laplace, you're going to use that table as well. Okay, and remember, keep in mind that Laplace is a linear operator, so any kind of constant multiplier, scalar multiplier, just kind of factors right out. So I always leave that little note there just to remember the rules of linear because it's been a while since we've seen Laplace. And so I think if you ask yourself from like 2 months ago when we first covered this, I think I would say I would say everyone kind of understood that, but just kind of make sure you review what it means to be a linear operator and how we can use that to our advantage. There's a few tricks that we actually did to do that. Okay. Okay, and of course, there's other details that you need to know as well. So, for cases where, we have forcing functions that may have a step or impulse function. Okay. So remember, we spent quite a bit of time talking about situations with those, right? And so, that's something you should be prepared for as well. Typically, when you have a step or impulse function, your Laplace transform and your inverse is going to involve a shift of some kind. Okay. Right. So we'll kind of quickly review the shifting theorems here today, but just make sure you know that as well. And yeah, so that's the whole process with Laplace. And so, I would definitely get familiar with this process. It's something to you can definitely expect a problem like this on the exam. So kind of knowing this process and getting the practice in, looking at the past homeworks. Remember with Laplace too, there's some additional notes I have on Canvas. Well, assuming that we can access Canvas again at some point. That has some additional examples with Laplace. So make sure you check that out as well. Okay. And so I don't remember exactly what weeks I posted them on, but you can look at just the overall file folder for our class and it should be in the folder for lecture notes. Okay. All right. All right. So with that said, I am going to jump ahead just for the sake of time, because the most interesting thing with Laplace, versus solving our differential equation normally is the fact that you can use step and impulse functions for our results. Okay, so let's skip ahead to there, just so we have time to do an example and we have time to cover probability and stats as well. Okay. All right, so let's first review kind of what exactly step and impulse functions are. Okay. So step and impulse functions are kind of specialized mathematical functions that we can use to model very specific engineering phenomena. Okay. All right, so a step function, just like its name, looks like a step, right? All right, so a step function is 0 up until a certain point, and then at when it's time for the step to activate, then the step function suddenly jumps up to a value of 1 and then persists at that value. And so the way that we describe this is we say our step function is u of t minus a. Right, where a there, that is the shift, or that is where we're applying our step. Okay. Okay, and an impulse is used to model a phenomenon that happens in an instant. And so the impulse looks something like this. And so it is a function that is zero everywhere except at a specific point. Right. And so at some value of time equal to b, then we have our spike. And so the function for this is delta t minus b. Okay. Okay. So with regards to step and impulse functions, conceptually, it's important to know or to understand what situations and what context that you're going to use a step and impulse function for. Right? So for instance, a step function, right? A step function is great for modeling scenarios where where the function is, or you have some kind of phenomenon that's either turned on and persisting or turned off at a certain. Right? So if you're looking at like an electric circuit, right? So electric circuits often have switches where you can switch a circuit on and off, right? Step functions are great in that sense. Okay. For impulses, like we just mentioned, impulses are great for phenomenon that happen very, very quickly. Right? So if you recall, one term that we used quite a bit when we were talking about Laplace was like a hammer blow, right? So any kind of forcing that is kind of maybe striking an object or striking your system very quickly, it's only leaving an impact for just a very short amount of time. That's something that you can model with an impulse. Okay. Okay. Good. So I'd say that's a good covering of at least the basics of the conceptual stuff. Of course, there's a lot more that we can talk about in terms of like shifting theorems and modeling of specific functions. But I think the next thing I want to do is an example, just to make sure that we get through this. So, but are there any questions just on Laplace in general before we jump into an example? Okay. All right. So let's do a simple example. All right, so for this example, this will be a good example of something that you might expect on the exam. Now the numbers for this one are going to be a bit simpler than what you can expect on the exam, just so I can get through it. But this is the kind of style of problem that you can expect. Okay. All right, so let's say that we are looking at a mass spring damper. And let's say that we are applying a ramp load on this mass spring damper only for a short period of time. Bless you. Okay. All right, so let's say that the differential equation for our mass spring damper is given by the following. So we have y double prime plus 4y prime plus 4y is equal to, okay? Right, and then our forcing function on the right-hand side is given to us by a piecewise function, okay? So let's say it's going to be 0. From 0 is less than t is less than 3, okay? Our forcing function a value of t from 3, which is less than t, which is less than 6, okay? Right, and then for everything beyond 6, the forcing is going to be removed, okay? So if it's going to be 0, again, back when t is greater than 0, okay? All right. We also need our initial conditions, and so let's say that our initial displacement, y of 0, we'll say it has a value of, we'll say it has a value of 7. And to keep things simple, let's say that we have a 0, 0 initial velocity. So y prime 0 would be 0. Okay, so for this problem, we are going to use Laplace to solve for y of t. Okay. So we want to solve for the solution to this differential equation using Laplace transform. And just judging based on the forcing function, we are going to need to do that. Because whenever you have a piecewise defined forcing function, you need to basically define this using step functions. And the only way for us to deal with step functions is to use Laplace. Okay. Okay, good. All right, so let's go ahead and get started then. So whenever you have a problem like this where your forcing function is defined piecewise, first step is always going to be to define your forcing function in terms of step functions. Okay. Okay, so let's do a brief kind of review in terms of how we do this. Okay. All right. So for our forcing function here, we have basically only one region where our forcing function is active, right? So our forcing function is only active from between t is equal to 3 and t is equal to 6, right? Every other time, our forcing function is equal to 0, so we can just ignore those times. Right? Okay. So what we can say from this is that our forcing function turns on at t is equal to 3. Okay. And then our forcing turns off at t is equal to 6. Okay. So the way that we can express that, remember, is you can say that we have t, which is our function. It turns on at t is equal to 3, so we're going to multiply this by our step function that is that starts at 3. So you have u of t minus 3. Okay. So this right here, this first u of t minus 3 is meant to reflect the fact that our forcing function turns on at that time. Okay. And then remember, whenever our forcing function turns off, we're going to subtract a step function that occurs at that time. Okay. And so since our forcing function turns off at t is equal to 6, we're going to subtract u of t minus 6. Okay. Okay, so that's our forcing function in this case. And so that right there is good. So before we take the Laplace transform, let's take this expression and plug it back into our original differential equation. Okay. And so we plug it back in, we get y double prime plus 4y prime plus 4y is equal to t u of t minus 3 minus u of t minus 6. Okay, good. All right, so now that we have that out of the way, we are now ready to take the Laplace transform. Okay. All right, so let's take the Laplace transform of every single term. And so remember, Laplace is a linear operator, so that means we can apply the Laplace transform individually to each individual term. Okay. So we have the Laplace transform of y double prime plus 4 times the Laplace transform of y prime, right? So you can see I factored the 4 out because it's just a constant, and so it doesn't affect our transform in any way. Okay. Plus 4 times the Laplace transform of y is equal to Laplace transform of t u of t minus 3 minus Laplace transform of t times u t minus 6. All right, and so now what you're going to do is you're going to look at your Laplace transform table. There's not too much for us to look up here, but although we do need to know the Laplace transform of each of the derivative terms, and then use that to apply our Laplace transform. Okay. Okay, so let's start with y double prime first. And so Laplace transform of y double prime, if you recall, is s squared big Y of s minus s y of 0 minus y prime of 0. Okay. All right, so that's another nice thing about Laplace is that the initial conditions for the function are incorporated directly into the formulation. So it's not something that we have to apply afterwards by ourselves. Next, we have the Laplace transform of y prime. So Laplace transform of y prime is s big Y of s minus initial condition on the function value, little y of 0. Okay. Plus 4 times big Y of s. Okay. All right, so that's the entire left-hand side of the expression there. So all that's good. Okay. Now we have to take the Laplace transform of the right-hand side. Okay. Now here it gets a little bit tricky, right? Because, let's look at the first term first. Right? So you have u Laplace transform of t times u of t minus 3. Okay. Now the fact that we have t minus 3 here, right? We have t minus 3 in a step function, so that means we do need to apply a shift. Right? In particular, since the shift is in the time domain, specifically, we're going to be using our second shifting theorem, or t shift. Okay. Now, one detail about the second shifting theorem is that if you're going to take the Laplace transform of some function multiplied by our step function here, they have to have the same shift, right? So in order to do this properly, this t has to have the same shift as our u there. Right, so we do need to modify our t function here just in order for us to apply that step. Okay, so as an aside, right, just as a reminder, Laplace transform is always hard to do in the review session. There's so many little details and so many little things you have to remember, right? Remember, there was kind of an alternate form for our second shifting theorem. Okay. And so what this alternate form basically tells us is that if we're taking the Laplace transform of f of t times u of t minus a, right? So basically taking the Laplace transform of a function multiplied by a step function, but the shifts are not matching. Right? Because ideally, when you would take the Laplace transform of this, you'd have, f of t minus a times u of t minus a, then you can apply the shift directly. But in this case, we don't. We have shifts that don't match up. Okay. Okay. So the way to deal with this is to take that shift and then apply it to the f of t, but you add it instead. Okay. And so in other words, we're going to take, right? We have an e to the minus as, and so this e to the minus as here, this accounts for our shift. right? So that accounts for our shift in the time domain, right? So remember, whenever you have a shift in one domain, whether it be Laplace domain or time domain, it's going to end up being an exponential function in the other domain. So the fact we have a shift of t minus a here means that we're going to multiply by e to the minus as, okay? And then you're going to take the Laplace transform of f of t plus a. Right? So you basically take that same shift, but instead of subtracting it from the function, you're going to add that shift to the function to kind of, undo that shift. Okay. Okay. So let's apply that exact methodology to our function up here. Okay. Okay. So we have a Laplace transform of t times u of t minus 3. Okay. Right. So this is a pretty prototypical case for this because we have our function t. That function does not have the same shift as our u here. But if we apply this the shifting theorem up here, we can see that this is going to be equal to e to the minus 3s multiplied by Laplace transform of t plus 3. Right. So we took our shift of minus 3 and we applied it in the plus form. So we added it to t in our function. Okay. And we can do this pretty easily. Right. So Laplace transform of t is 1 over s squared. Laplace transform of a constant is just 1 over s. And so this is e to the minus 3s times 1 over s squared plus 3 over s. All right. And then we can do the exact same thing for the other term. So if you look at our other term here, our other expression here is t times u of t minus 6. So that's very similar to what we have up here. And so we take the Laplace transform of t u of t minus 6. Okay. We apply the exact same rules, except now we have a shift of 6 instead of 3. And we have e to the minus 6s times the Laplace transform of t plus 6. Right, and so that's equal to e to the minus 6s times 1 over s squared plus 3 over s. 6s, thank you. Yes. All right. Good. So let's take these two expressions and let's plug them back into our differential equation. Okay. And then we'll finally get an expression that we can solve for y of s. All right. Before we do that, any questions on this so far? Oops. Okay. All right. So let's put this all together. So first, let's take our initial conditions and plug them in. Right. So we know from our problem here, our initial velocity is 0. So that means our y prime of 0 here is going to be 0. Okay. And then our little y of 0 is going to be 7. So let's plug that in for here as well. Okay. So we put all that in combined together with our forcing function, we get s squared y of s minus 7 7s plus 4s y of s minus 7 times 4, which is 28, plus 4 y of s is equal to e to the minus 3s times 1 over s squared plus 3 over s plus e to the minus 6s 1 over s squared plus 6 over s.
Is it plus or is it I maybe just so complicating it, but up on top where we got t of the step minus the step.
Mhm.
Was it, do we not take the minus, put it there? And
Oh, yes, you're right. I did miss that minus. Yeah, so this should be a minus here, so I did miss that. Thank you. All right, so now that we have this, we can now solve this algebraically for y of s. Okay. All right, and so on the left-hand side, let's keep every term with s here, or let's keep every term with y of s. So you have y of s multiplied by s squared plus 4s plus 4. And then everything that's not y of s, we'll move it over to the right-hand side. Okay. So we have 7s plus 28 plus e to the minus 3s, 1 over s squared plus 3 over s, minus e to the minus 6s, 1 over s squared plus 6 over s. Okay, so let's divide everything by that quadratic term on the left-hand side. So we can then solve for y of s. So y of s is equal to 7s divided by s squared plus 4s plus 4 plus 28 divided by s squared plus 4s plus 4 plus e to the minus 3s times 1 over s squared times s squared plus 4s plus 4 plus 3 over s times s squared plus 4s plus 4 minus e to the minus 6s times 1 over s squared plus 4s plus 4 plus 6 over s times s squared plus 4s plus 4. All right. So I take back my earlier statement. A problem like this would probably be a little bit too intense for the exam with how many terms that there are. Yeah. I was fooled a little bit into thinking that y squared plus 4y plus 4 is going to be simple. But the hard part here is going to be in the partial fractions, not necessarily in the Laplace transforms. Okay, so now that we have this expression for y of s, we can now try to invert this in order to solve for y of t. Okay. Okay. But unfortunately, and one thing that you should notice is that this expression here is not really capable of being inverted, okay? Because nothing like this matches our table. Okay. So what does that mean? So that means that we do have to do a partial fraction. All right, so we're going to do a partial fraction decomposition of these terms in order to get them into an expression that we can, actually invert. Okay. Okay, so unfortunately, we don't have time to do partial fractions on everything here, but I did want to do at least one of them, just so that you can kind of see what that would look like. Okay, so let's take one of the more interesting ones. Let's take let's take this one here. Right? So let's do partial fraction decomposition of that term right there, just so that you can kind of remind ourselves what this looks like, and then you can kind of go from there. Okay, so we're going to take partial fraction decomposition of 6 over s times s squared plus 4s plus 4. Okay. All right, so this one is quite interesting, right? Mostly because we're going to have a double root here. Because if you notice, s squared plus 4s plus 4, right? If we factor that into, if we factor that into, its factor terms, that's going to be 6 over s plus 2 quantity squared, right? And so we have a double root here at s is equal to -2, right? And so that does affect how we do our partial fractions. And so let me kind of bring up the rule real quickly, just so that we can all look at it together. Okay. And so in a situation like this, our partial fraction decomposition is that we're going to first have one term for s. Okay, so we have a over s by itself. Okay. Plus, we're going to have two terms. So one term for the s plus 2 by itself. Right. And then we have another term for s plus 2 quantity squared. Okay, so remember, you need to have both when you have that double root. Okay. So when you do partial fractions, first thing we're going to do is we're going to multiply this entire expression by the denominator. Okay. And so we do that, we get 6 is equal to a times s plus 2 quantity squared plus b times s plus 2 plus c times s. Okay. Yeah.
When you do the stuff where you have something like cx plus d in the numerator.
So you do that when you have an unfactorable quadratic expression on the bottom. So let's say that we had, 6 over s times s squared plus 5s plus 4, right? So this 5s plus 4, you can't factor that. And so this would be, a over s plus bs plus c over s squared plus 5s plus 4. Right? So eventually a term like that, you're going to have to do completing the square in order to get that into something we can convert. But since this one we could actually factor, right? So this one we factored from s plus 2 quantity. We went from 4s squared plus 4s plus 4, and we got that to s plus 2 quantity squared, right? And so for that, we can break it up into, one term with just one of the roots and the other one with two. Yeah. Mm-hmm.
And that's where you have to be squared.
Exactly. Yeah. Yeah. Okay. All right. So let's go ahead and continue this. So next step, right? Next step here is we're going to FOIL everything out, right? Because eventually what we're going to do is we need to solve for the constants a, b, and c. So you have 6 is equal to a times s squared plus 4s plus 4 plus b times s squared plus 2s plus c times s. Okay. All right. Then from here, what we're going to do is we're going to group the like terms. Right. According to the powers of s. Okay. All right, so we do that. We get 6 is equal to, let's do all the s squared terms first. So for s squared, we have an a plus b. Okay. Next, we have all the s terms. And so for s, we have 4a plus 2b plus c. Okay. And then for the constant terms, we have just 4a. That's the only constant term that we have. All right, good. So now that we've set this up, we can now set up a system of linear equations to solve for a, b, and c. Okay. All right, so we're going to set up an equation for the s squared terms on the left-hand side and the right-hand side. For an s term, for the s term on the left-hand side and the right-hand side. And then our constant term on the left-hand side and the right-hand side. Okay. Okay. So let's set up the equation for s squared first. So for s squared on the left-hand side, we don't have any expression there. Right, so on the left-hand side of this equation, we just have 6, which is the constant. So left-hand side for the s squared equation would be 0. On the right-hand side, we have a plus b. So whatever we get for a and whatever we get for b, they have to be same magnitude, opposite sign, because their sum has to be 0. Okay. For the s term on the left-hand side, we have also 0, because there's no term that depends on s. And on the right-hand side, we have 4a plus 2b plus c. Okay. And on the last term for the constant, on the left-hand side, we have 6. On the right-hand side, we have 4 times a. Okay, good. All right, so thankfully for this system here, this is fairly simple to solve because we can just go our third equation, first equation, second equation. Okay. So from this last equation right here, we have 6 is equal to 4a. We divide both sides by 4. That gives us an expression for a. We get a is equal to 3 halves. Okay. We plug 3 halves into our first equation here. And so we get from our first equation, if a is equal to 3 halves, that means b must be minus 3 halves. Right? Because their sum has to equal to 0. Yep. Yep. So then we plug everything back into our second equation here. We plug in that for that, that for that. And what we get for c is 4 times 3 halves, which is 6, minus 2 times 3 halves, which is 3, plus c is equal to 0. Right? So c is equal to minus 3. Perfect. Okay, so let's plug all of those coefficients back into our partial fraction here. Okay, so you have 6 divided by s times s plus 2 quantity squared is equal to 3 halves over s minus 3 halves over s plus 2 minus 3 over s plus 2 quantity squared. Okay. All right, good. All right, any questions on how we did that partial fraction decomp? Very fortunate. The numbers for this actually turned out pretty nice. We didn't get any kind of weird fractions or decimals. Okay, All right, so now that we have this, our last step here is just going to be to invert it. And so let's see how we invert this term before we move on to probability and stats. Okay. Now we can't forget, right? Remember, we pulled this term here from this part of our Laplace expression, but technically this part here was multiplied by e to the minus 6s, right? So I didn't factor that into our partial fractions because, well, first of all, it doesn't affect our partial fractions. Because remember that e to the minus 6s there, all that's going to do is that it's going to apply a shift in the time domain. Okay, so let's not forget this e to the minus 6s that has to be out here as well. Okay, and so it's e to the minus 6s. This is going to cause a shift in the time domain. Okay, so again, this is going to be an application of our second shifting theorem. So we have a very specific way of dealing with this. And so at the end of the day, we are going to have an expression that shifts by 6, right? But remember, the way that we did this was that we first, when we're taking the inverse Laplace of something with a shift, we first took the inverse Laplace of what we call our base function, right? So we're going to take the inverse Laplace of everything that's in there in parentheses, and then we're going to apply the shift after that. So first, we're going to take the inverse Laplace of these base functions. Okay. Then apply shift. Okay. All right, so let's go one by one through these expressions here, and let's take their inverse based on the table values here. Okay, so first we have the inverse Laplace of 3 over 2 times s, right? So 1 over s is the Laplace transform of just 1, right? And so the inverse Laplace of that is very simple. It's just 3 over 2 times 1, which is 1. Okay. So 3 over 2 is just simply the inverse Laplace of 3 over 2 over s. Okay. Next, we have the inverse Laplace of minus 3 over 2 divided by s plus 2. Right? Okay. So just like the first term there, we're going to have a minus 3 over 2 that comes out, right? So that's just simply a constant term that has to come out there. Okay. Next, we have inverse Laplace of 1 over s plus 2. Okay. Now, the fact that we have an s plus 2, remember, that tells us that we have a shift. This is a shift in the s domain. Okay. And so shift in s domain means that we are going to apply our first shifting theorem. Right, so all of the characters. So we met a lot of different theorems and equations and different terms in Laplace. They're all kind of coming out in this example. That's kind of why I chose it. Okay. Okay, and so remember, to deal with the shift in the s domain, you're going to multiply by an exponential function in the time domain with the same shift. Okay. So e to the minus 2t, right? So that e to the minus 2t there, that takes care of the s shift. Okay. Right, so that that first shifting theorem results in e to the minus 2t in the time domain, right? And so then after that, we're just taking the inverse Laplace of 1 over s, which is just 1 as well. Okay, so the inverse Laplace of that second term is just simply minus 3 over 2 times e to the minus 2t. All right, and then we have our last term. So we have our last term, we have a minus 3. Okay. Again, we have a shift. And so we have an s plus 2 inside there. And so that's going to be a e to the minus 2t. Okay. Right, so that's going to get rid of the shift in the s domain there. So that's going to be, now we have minus 3 over s squared. inverse Laplace of S squared is just, inverse Laplace of 1 over S squared is just T. So our last term there is minus 3 times e to the minus 2t times t. And then finally, we have that that S shift out there as well. Okay, and then final step here, we're going to apply this, apply the T shift. All right, and so to apply the T shift, we're going to multiply this entire expression by a step function with the same shift. And then we're going to replace everywhere we see T, we're going to replace it with T minus 6. Okay, so you have 3 over 2. There's no T there. Minus 3 over 2. E to the minus 2. T minus 6. Right, so I replace the T in that exponent by T minus 6. Minus 3 times E minus 2. T minus 6 multiplied by T minus 6. Okay. And this whole thing we're going to multiply by U of T minus 6. Okay.
So the U of T minus 6 is a formality, right?
This one you need it because you know, if when we take the inverse Laplace of the other terms, we're going to have some terms that are shifted by 3, some that don't have a shift at all. So yeah, this time we actually, yeah, if everything had the same shift, then it would be a formality. But this time you would end up with results with different shifts. All right. So what started as a somewhat innocent problem kind of ended up being a big result. And so it took us half an hour to cover this example, and we only did one part of it. And so technically we have to do the all the other terms here as well, right? So something like this probably not going to show up on the exam because this is pretty long here. But you can expect a Laplace ODE of some extent to be on the exam. Okay. All right, any questions on this before we move on to probability and stats for the last 15 minutes of class? Okay, all right, so for the last 15 minutes, let's review probability and stats. Okay. Okay. Now we covered quite a bit of probability and stats, and so you know it may not seem like it just because you know we're kind of just jumping around different topics, but we've been covering this for like a solid 3 weeks now, and so there's quite a bit to cover. But in terms of what I'm expecting you to know for the exam, now conceptually, you know anything that we covered in probability and stats is fair game in terms of the conceptual questions. And so I would definitely review all the lecture notes and the study guide for that. But in terms of the problem that I'm going to ask you to do on the exam, there's really only 2 that I can realistically ask you to do, which is either to compute a confidence interval or do a hypothesis test. Okay. Realistically, you know, that's the only thing I could really test you on because you know you're not gonna have access to Excel, and so you're not gonna be able to plot anything. So there's no regression analysis that's going to be at least not in problem form. I may ask you a conceptual question on regressions. But in terms of the problem, so you know, a good 15% of the exam is going to be one of these 2 topics here. Okay. Now you guys are working on this for the homework, right? So problem 2 on the homework, I'm having you compute the confidence interval of your heart rate. And then for the second one, problem 3, I'm having you do a hypothesis testing on the value of gravity, G. Okay. Now in the homework, you know, a big part of those problems is that you have to produce the data yourself. I'm not going to ask you to produce data on the exam, so I shouldn't see people kind of dropping their pencils on the exam, you know, with the stopwatch, right? So I'll provide you the data. Right, so it's probably going to be anywhere between 10 and 15 data points that I'll give you. Okay. And then based on the data, I want you to compute either a confidence interval or hypothesis. Okay. Now, to do these problems, you have to kind of know a few things, right? Right. And so this is kind of consistent between both of the types of problems I'm going to ask you to do. First of all, you need to identify whether the variance for the problem is known beforehand. Okay. And so how do you know? Well, there is a more philosophical way to know, but for the exam, just to keep things simple, if the variance is known ahead of time, I will tell you what the variance is. Right. If you recall from our in-class examples, usually for situations where your variance is known is for, when you're taking measurements with the very known uncertainty, right? So the example that we did in class that we kind of covered extensively was, maybe you had a ruler, right? You were measuring the length of a phone, and that ruler had a very known precision, right? So there's really only, in those situations, there's only one factor that's leading to uncertainty, which is just the measurement device. Okay. But for the exam, if it's known ahead of time, then I will just give it to you. Okay. If the variance is not known, okay, you will need to compute it yourself. Right. So the problem may not even say anything about it, and so it may not mention anything about the variance. And so if the problem doesn't mention it, then you can assume that the variance is unknown and something that you're going to have to compute from the data. Okay. Okay. And remember, so whenever you compute the variance yourself based on data, that's only an estimate of the variance. It's only an estimate based on kind of what you've computed. And so we call this the sample variance. Whereas if the variance is known, this is known as the true variance. Okay. Right. So make sure you know the difference, and make sure you know the formulas to compute these. So, just if everything else on the exam, I would say it's very useful to bring your calculator for this problem specifically, because you're going to be asked to compute, the mean of a data set. You might be asked to compute the sample variance of the data set. And so that's going to be much easier to do with your calculator. Okay. Of course, you can do it by hand, but it's generally not, it's going to take you time. That's the only thing. Okay. Now you do have more time on the final exam, but in general, you don't want to be kind of dawdling for, at any given point. Okay. All right. Now, in terms of the problem solving methodology, this does affect how you're going to be looking up a certain variable, right? Right. So both confidence intervals and hypothesis testing, what you've probably noticed is that you're going to make use of a table of a cumulative distribution function. right? So both confidence intervals, you're going to compute some value of f of c. So f of c, remember, is a metric that depends on two variables, right? Or I should say, let me kind of rephrase that. So the formula for f of c is usually only dependent on either your level of confidence in your results, or the level of confidence that you want to express, or the value of significance if you're doing hypothesis testing. Okay. Okay. So that's one thing you have to kind of be careful of. And so, the two techniques for confidence intervals and hypothesis testing, they do have a lot of similar steps. But one of the key steps in that process is how you compute f of c based on the type of problem that you have. Okay. All right. So for confidence intervals, the f of c is computed by 1/2 1 plus gamma. Okay. For gamma, this is our level of confidence. Okay. Our level of confidence expressed as a decimal that's usually that's less than 1, but greater than 0.5. Okay. But for hypothesis testing, it gets a little bit interesting because it depends on the type of alternative that you're looking at. Okay. All right. So for f of c here, it's either going to be alpha or 1 minus alpha or 1/2 alpha. Okay. And that depends on the type of alternative that you have. Right. So the situations where you use an f of c of alpha, this is when you have a left-sided alternative, or in other words, your rejection region is on the left-hand side. It's going to be 1 minus alpha when you have a right-sided alternative. Okay. And it's going to be 1/2 alpha, or I should say 1/2 alpha plus, not plus in the literal sense, you're not adding these, but you're going to do two cases. Right. So remember, this is what happens when you have a two-sided alternative. Sorry, it's a little haphazard. I'm just keeping an eye on the clock. I just want to make sure I kind of cover as much important details as I can, in kind of the short time that we have remaining. Okay. Now, one important thing to know is that if you are given a problem with under hypothesis testing, choosing your alternative is going to be a very important factor. So that's not something that you can expect to be given, right? And so if I do give you problem hypothesis testing, you should be able to determine which type of alternative is most suitable for this type of problem. So we're going to have to use a little bit of ingenuity, a little bit of kind of reasoning to kind of, to make that decision. Okay. And remember, because the main kind of thing that you're determining with the alternative is you're determining what your rejection region is going to look like, right? So, do you care more if the result is, much less than what you hypothesized, or do you care more that the result is much greater than what you hypothesized, or do you want to be kind of right in the middle? Right. So for example, right? Right. One example that we talked about in class was measuring or hypothesizing the breaking strength of a structural wire. Okay. Right. So we're ordering wires from some manufacturer, and they're claiming that their breaking strength is, let's say 200 pounds, right? And we want to test that hypothesis. Indeed, in this situation, if the strength of the wire ended up being more than 200 pounds, that's something that we're actually happy with. And so, we're not going to reject the wire because it had too much, strength. Okay. Right. Right. So think about, if you're ordering food, right? You get chicken McNuggets, right? You're not going to return the McNuggets if you got an extra one, right? So that's something that you're happy with. And so in that situation, then your rejection region should be on the left, right? So you are going to be upset if the strength wasn't up to what the manufacturer was stating, right? And so in this situation, you'd pick a left-sided alternative. Right. Right. Another example. So one thing that we talked about, hypothesis testing is used in quality control. And so one thing that you can test for in quality control is the amount of defects in your product that you're producing. Right. And so in that situation, you're going to have a right-sided alternative, because if the magnitude of the defects gets above a certain threshold, that's when you reject your hypothesis and you go back and go and change your process. Okay. Right. So part of this problem is, if you're given one like this, is to kind of really read through the problem and kind of think about, what is the worst case scenario? What is one that is going to lead to a negative result? And that's going to determine the type of alternative that you use, and that's going to determine how you compute f of c up here. Okay. Okay. Any questions on this? Yes.
For their quality control, why would it not be a double-sided?
You could, right? So it depends on how you measure the defects. And so by defects, I mean, I just kind of use a general term, but maybe they're measuring, how the the amount that, maybe is, whatever you're cutting, maybe the amount was over that, right? Yeah, so I think in most cases, if you're doing something precise, it would be a double-sided return because you want it to be right precise. But in this case, maybe the type of machine that you're doing, it has a more tendency to add more defects rather than take it apart. Yeah. So it is very kind of context dependent. And that's one I kind of just try to make up very quickly right now. But yeah. You could also make the argument that's a double-sided too. So I think on the exam, if you can make the argument one way or the other, I'm not going to be rigid in that it has to be one. Okay. All right, so I apologize we couldn't do an example with this, but I did want to kind of run through all the important factors to kind of take into account. So for the last time, guys, thank you guys for coming today. I know I said this on Tuesday, but it's been a great semester. You guys have been a great class. I will see you guys next week on the exam. And if you have any questions about anything, just feel free to email me or stop by office hours next week. So thank you guys, and I will see you next week. Tuesday. Yeah, Tuesday, 5 o'clock here. Yeah.
I totally missed which Friday it was due as I was due last Friday, and so I just submitted it.
Yeah.
At that point, we still have not gone over regression analysis versus relation analysis, which I just didn't know what is.
Yeah. Okay. Yeah.
Because I just don't know if I answered that question right.
Yeah.
Because I think I just didn't.
Yeah. So I think if you kind of you're already kind of starting with prep for the final, I think it's okay. Not somewhere I kind of just look at it very quickly because everyone's answer is so different. I don't look at it too carefully for the last one. No, not a problem.
Preparation for this final. You mentioned beginning class, but it sounds like OD will be the first order OD will be mixed in so with Laplace trying.
Oh, that's your
trying to ask.
Probably not. So probably the Laplace problem will be something like what we did in exam today. It'll be a second order OD. First order would be its own top.
It's like one part instead of four.
Yeah.
Or six in this case.
Yeah. It'll be a little bit easier.
Okay, no problem. Sounds good. So then, and then Fourier transforms. Okay, Fourier transforms. In my mind, it bleeds over a little bit with the other Fourier stuff.
It does. Yeah, there is a lot of overlap.
Oh,
so Fourier transform specifically is the one where we do the integral. It's not the series, and so we're not computing coefficients. We're actually computing a function of omega, a function of frequency.
Can I pull that up really quick?
Yeah.
Sorry.
Mm-hmm.
Okay, so let's kind of cosine
Yes.
sine Fourier transform.
Yeah, so you can see for these ones, we're getting an actual function of omega. Whereas for the coefficients, we have functions of, they weren't functions, they were coefficients and n, right?
Right.
So these ones don't have.
They go back in front of another function, in
Exactly.
front of another sign, in front of another.
Exactly.
Versus this one is just going to be the standalone function right here, as opposed to being added back in.
Yes.
Okay.
Yes.
Okay, so yeah, just one page notes essentially. Thank you.
Yeah, no problem.
But if I email you, can you send me the homework 6?
The homework 6
or the 7? What's the one right now?
Oh, because Canvas is down. Yeah.
I haven't started it.
Yeah. I don't know how long Canvas. It seems like it's a pretty big attack. So yeah, if you haven't started it. Send me. I can send you the PDF.
Okay, I appreciate that.
Yeah.
Thank you.
Mm-hmm.
Have a good
You too.
weekend.
You too. Oh yeah, Pablo. So since Canvas is down, I don't know how long it's going to be down, but forever long it's down. I'm going to extend the due date for the homework 7.
Oh, okay.
Yeah, so at the very least, I think original due date was tomorrow, but then it's going to be pushed back to Saturday now, at the very least. But if Canvas continues to be down tomorrow, I'll push it back to Sunday.
Okay. Yeah, because I just got my professor emailed me. He's like, oh yeah, I don't know, so I'm pushing everything a week in advance. I'm like, oh, what the heck? So I came to ask you about that question.
Sorry, Pablo. I don't have sound here. In the
no!
I see that you're talking, but there's no speakers here. Yeah, I'm gonna push it back too. Yeah. Yeah, I think that's the only reasonable thing, because no one can turn anything in right now because the canvas is down. Yep. All right, Paul, we'll have a good one. We gotta go to my next class.